a charged particle is revolving in a circular path, will it produce any magnetic field? It is moving in a circular path with a constant speed v. So shall I say current I is flowing? Let A be the radius. Then how you define current? Current it as charge by time. And what is the time period? As it is moving with a constant speed. So therefore time period 2 pi A into V. So this is QV by 2 pi. So this is not a ring. Huh? This is not a ring. So what is charge particle? Charge particle, it is flowing in a curved path, not a ring. It's not a current carrying ring. Charge particle, it is moving in a circular path of radius c. Then, so we define the current I flowing that one. So what is the dipole momentum of this revolving charge particle? No. So what we are putting m bar of revolving charge particle. So what is the basic definition? Current into area. What is the current? Current we have defined it Q omega 2 pi a. This is pi a square. So therefore this will be QVA by 2. This is the dipole moment. This is the expression for the magnetic dipole moment of revolving charge particle. What is V? V is the speed of the charge particle. Now you can ask, what is the use of this? Where the hell we are going to get this revolving charge particle? To study magnetism due to a material. Because how do that magnetism of a object will come? Ferromagnet. How that ferromagnetism? Then paramagnetism. So usually what is the substance made up of? Revolving charge particle and atoms. No? So the revolving charge particle, will they contribute any magnetism? Definitely. Looking at this, a charge particle revolving in a circular path will behave like a magnet. Like that, for an atom, several revolving charge particles will be there. So they will contribute some magnetism. Like that, to study the magnetic properties of a material, we need all this background. For that purpose, we are introducing all these things. Magnetic dipole moment, what is the use of advantage of this? To study the behavior of materials, magnetic materials. There's the one thing. Next, again, the application. Current carrying loop will experience a torque or a force that we are going to use in the construction of meters, several analog meters. There's a background. And now, instead of revolving, it's a negative charge particle. So just show that current in opposite direction. That's all. No. And now, instead of this, let me rotate a charged rod. I will rotate a charged rod. Now dipole moment of rotating charged rod. So let the charge be deposited. Go back to electrostatics, it's a finite rod. Length of the rod is L. Total charge, let it be Q. I'm rotating about one end. Then what is the dipole moment? And let M be the mass of it. What is the dipole? Magnetic dipole momentum of it. So let me assume a small element here. So this small element, what it do? It is going to revolve in a circular path. So let the dx charge of that be dq, and it will have a speed v, and it's going to move in a circular path. Then what is di first is equal to dq by t. So what is t time period? 2 pi by omega, or dq omega by 2 pi. What is the dipole momentum of this small element? dm is equal to di into pi x square. No, look at the element. It will move in a circular path of radius x. The small element, it's going to move in a circular path of radius x. So di equal to pi x square. So what is di? Let me substitute here. This will be dq omega 2 pi x square. So further this dm is equal to dq is what? Lambda into dx omega 2 pi x square. So let me eliminate 2 pi. So lambda omega by 2 x square dx. Dipole moment 0 to L. So lambda omega L cube by 2. What is lambda? Charge per unit
That's
length.
6.
6 will come. So this should be Q by L. So Q omega L square by 6. What is the, this is what? Magnetic dipole moment, no? This is a magnetic dipole moment. What about angular momentum? Let's calculate the angular momentum. So what is the angular momentum of this rotating rod, which is equal to small l, I'll take it, because angular momentum symbol is okay, no. What is the angular momentum? We define it as I into omega a dash, you write it. Angular momentum L a dash. This should be equal to how much? L a dash I a dash into omega, which is equal to ml square by 3. What is small m? Small m is mass. Capital M is dipole moment. Capital M is dipole moment. So this small m naught, I'll write it because again. So let me put all the symbols in order. What is m naught? Mass of the rod. So let's take the ratio of these two. What do we get? Ratio of dipole moment to angular momentum. This should be equal to Q omega L square by 6 m naught L square omega by 3. How much I'm getting? I'll end up Q by 2 m naught. What is m naught? Mass of the rod. Similarly for charge particle also, let's go back. I think just see once. So what is the ratio of dipole moment to angular momentum of this non-conducting charge rotating system? Charge divided by twice of its mass. For charge particle also, what is the angular momentum? About 2. This should be equal to m a square into omega. So m by L naught Q. Okay, this is like I should write V equal to A omega, no? So this will become A square omega by 2. Means either you take charge particle or rotating rod or rotating disk or any non-conducting charged object. If it is rotating about any axis, the ratio of its dipole moment to angular momentum should be equal to charge divided by twice of its mass. I think this is, I think, which will be very easy to calculate. I think we have already explored. We already explored what the angular momentum concept. So which will be very easy. Angular momentum is somehow we can find out very easily. So dipole moment will become easy for us to calculate. So therefore, finally, what I say, any arbitrary shape you can see, arbitrary shape, non-conducting. It's having a charge q. It's having a mass m. Then let it rotate about any arbitrary axis, not something I'm just showing axis like this. Omega. So what is the ratio of angular moment, dipole moment to angular momentum? You call this is P dash. About any axis. Axis P dash can be the axis. This is the axis. This should be equal to how much? Total charge by the mass. Fine. So this is the one thing which you have to remember. You have plenty of numericals. Try to solve. It's all about the geometry, no? So what I do, uniform charged sphere. I will rotate about an axis passing through diameter. Then they'll ask you what is the ratio of that. If you know total charge mass, the ratio will be q by 2. Just verify, see once and come out of that. Because definitely in exam, they don't ask anything straight away that questions. So just in SURMA, there are 8 numericals are there of different shaped objects. They are rotating about an axis. Just see the geometry involved. Cone also I can ask you. I can ask you sphere. I can ask you pyramid. About different axes, I'll rotate this one. So if you know how to calculate angular momentum, I think you can get other one. Means what is the advantage of this? If you know any one, you can calculate the other one. So angular momentum will be very easy for you to calculate. Or dipole moment, left to you. You pick up either one. The ratio should be q by 2m only. Okay, this is about the thing. So which is just we don't have much application, just only integration based questions are there. Try to manage few. On the Friday, I'll discuss 2 or 3 different shaped objects, how to calculate dipole moment. So let's go for the analog, like application part.